Yes, I can hear you.
Yep, I can.
Yeah, I heard you pronounce my surname, which is very difficult. You did a great job.
Thank you.
Yeah, it's a tough one. Let me share my screen. All right. Okay, I'll try to keep this part quick. You already have a neural network related interatomic potential session by now. I missed that, I'm sorry. So I might have some overlap, some repetitions. I will try to pass it quickly. So we have been working on PANNA since 2015 on our little corner as side projects. We're mostly DFT people from Sissa, Italy. Back then we were, now we are all over the place. You'll see my co-developers, University of Toulouse, École Normale or Berkeley. And these are the two professors that were very supportive and helped us not waste our time in things that didn't really matter, basically. That was their biggest contribution. Because once you enter in this world, there's just so much you can optimize, so much you can implement. And they kept us, I would say, on point. Okay, so what we wanted to do in PANNA was to really lean into the Hohenberg-Kohn theorem. So we are DFT people, we know how DFT works, but we were very much focused on the Kohn-Sham part of things. If you are a DFT modeling person, you would know the Kohn-Sham allows us to map a ground state density to the total energy and all the properties we can calculate from total energy. If you take a step back, actually the first theorem that was famous for DFT was Hohenberg-Kohn. So where we know that the ground state energy and the potential of the nuclei for an n-electron system has a map, a one-to-one map in between. So if you really stick to this idea that if I know the potential of the nuclei and how many electrons I have in my system, I know the energy, that is a problem that you can recast, like saying, okay, if I know where my atoms are and what species they are, I can find the potential. This is straightforward, but I can also find there exists a function at least to give me the total energy of the ground state, and then the forces, elastic properties, spectroscopic properties, etc. So if you just look at this problem as a function approximation, neural networks do a great fit for that. Let me open this. While the Kohn-Sham equations allow us to calculate this map for all physically meaningful potentials and for any n, you can ask with a neural network as an approximator, you can say, can you approximate this function, not for all the potential types, not for all possible number of electrons, but for some subdomain of this space. So actually neural network solves a known problem. We know that a solution exists, a map exists, and we know that this can be simplified because we're not trying to solve in the whole domain where the solution exists, but limiting ourselves to a part of it. Sorry. Okay, so this is our idea. We start with the species and where they are, basically the atomic positions and which species we're talking about. What we want to reach is the total energy. And the neural network is this approximator in between. Okay, so you have seen some kernel methods, you have seen neural networks. I will give you a quick take on why I think we use neural networks and what are good and what are bad about them. So they're very flexible. They can really fit very complex functions. And we know that. We know already from all the neural network success stories outside physics too. But what I like in physics is that the cost does not increase with the data size. And I think this is very crucial. That means today you made a network, it worked for some system, but tomorrow you notice that a part of the structure space, a domain that you did not cover in your data, network did not do a good job there, you can just add more data. It doesn't change the cost of your network, and you can really go to a better and better network over time. We have done this in the past, and it really helped us to do that. We thought that we have covered a certain part of the phase space, and we could use a network that we built 2 years ago, back with some more data, and we're able to tackle a harder problem. And we still paid the same cost for our potentials. So that's very nice, I think. That is, of course, the data is always costly, but if you're trying to solve some complex function with high accuracy, like if you're really focusing on accuracy, this is a really great advantage of networks. Training is always not straightforward. So it's going to take you some getting used to understand where the training might fail. That's just some learning curve, I would say. And a very big open question for neural networks right now, outside physics as well as in physics, is how to measure our error bars, like what's our uncertainty. You might have heard about the committee methods, where you have like a bunch of networks trained and trying to guess, and you can try to understand how much to trust in your networks based on how much they agree. The committee agrees on the decision, but this can be very misleading. We have seen examples of this in our networks, in other people's networks, that you can have a bunch of committee members that are very confidently making the same mistake. So if some kind of bias is embedded in your data, all your networks might show this bias. And so these committee methods might not really work. That's something to watch for. Anyhow, this uncertainty measure thing, error bar thing is an open question. If neural networks are your thing, and if you have some ideas, like you can really help out a lot of us on that. Okay, so about the cost of the network potentials, in my experience now, quite a few years, I would say, I can safely say for many systems I work with, it's somewhere in between a force field and a DFT calculation. I would say like 3 orders of magnitude more than force field and 3 orders of magnitude less than a DFT, but of course it depends a lot on your system. So you will be the judge of that, if it is really worth doing. And maybe final thing that I wanted to mention, like neural network potentials are quite established for a lot of systems right now, especially a few species systems, some metals, small molecules, semiconductors, allotropes. If you're doing that kind of work, the amorphous systems, we really have really good potentials, and you can use multiple codes for that. PANNA is just one of them. I think it needs a little bit more research optimization polishing is about the charge systems. We again have good basics there. We have it in PANNA, and other people have in other codes where we have networks that are aware of the local charges. What is, I think, needs the most attention from the developers and from the physicists who are theorizing this stuff is magnetic systems. But there the problem is coupled because DFT also has a lot of issues with the magnetic systems. So we often hit the DFT limit before we hit a neural network limit there. So that is still an area that needs a lot more research, I think. If you have any questions, you can interrupt me, by the way, I'm just going as fast as I can, because normally we give these tutorials and talks for a whole PANNA one-day workshops. So I'm trying to give a very compact 1-hour version of that to you.
Can I ask a question?
Sure.
If you
go ahead.
Yeah, so I wanted to about committees. I mean, if you it also depends on how you sample, how do you create them, right? If you're just subsampling on your training set, then a committee is not meant to give you an uncertainty due to the bias, whereas it's only supposed to give you an uncertainty due to lack of insufficient data. So in that case, if your committee error is 0 and you still have a remnant error, that
right, and you
tells
have
you
to
the bias, right? I mean,
yeah, you have to be careful. If it is a bias that you have, let's say, coming from DFT, then all your calculations have that bias, for example.
Yeah.
Right, if there's a particular DFT bias that, I don't know, when you have negative pressures, your DFT calculations have issues, then it will show it in any neural network that is seeing that kind of data, but then it is your diff. So it's just a bit harder to, I think, tease apart where the bias is from. And that's how, when we see in committees, when committees confidently make the same mistake. Sometimes it is, if you did not change the activation functions across the different networks, you might see this doesn't happen all the time. But I just want to say it's not okay that I say, okay, I made 10 neural networks, they all agree in this result, and yes, so this should be good. It should be done more carefully, and I'm not sure people are doing this carefully enough right now, but we're all learning. So yeah.
Yeah, I agree that the error in committees doesn't include the bias at all. So yeah.
Yeah, there are a lot of possible sources of bias also.
Yeah.
Right. By time, I hope we're going to develop more better practices. I know we're going to be able to see these things more clearly. Okay, so 2 examples I want to give you that we have done with PANNA, that you can also see this published in archive papers and some other talks that I have given or my colleagues have given. What I want to get your attention is that we don't do active learning with PANNA, but we do something different. This is one. And this is not something novel that we didn't think about it first. Other people have been doing it too, which is starting with a neural network and then sampling the space with either, in our case, with evolutionary algorithm or just with MD calculations so that you have more data. And then on part of this data, you can check whether these are new structures for you that will enrich your data set or not. And then you can, in a subsection of them, you can do DFT. So because you want to do as few DFT calculations as possible while giving as much data for your network to learn from. Neural networks are generally large, so that we're talking about thousands, tens of thousands of parameters. So data helps, and it's also expensive. So you don't want to do too much of it. And there are many techniques. We do clustering in between to reduce the number of structures that we have to do the DFT. We start with a force field generally, and then refine on that with some DFT calculations after. Sometimes we will start with a simpler functional and then go have a more expensive functional in later steps and just train the last layer of the network. So you can try to make best use of the data. What I want to show here is that in this work, we really try to look at all possible carbon structures we could think of. It's very hypothetical structures, like none of these things are stable. You can see what they look like, right? So these super porous ones, weird combinations. The good thing is that, of course, then we have a very rich data set, and network has seen very different combinations, very different forces. And this richness, though, comes with I don't say disadvantage. It makes your errors look very high. And what I mean by that is that when we measure our errors, we measure them on the data that we have. So if you have a data set that is, I don't know if you can see the bottom of this image, but I'll try to explain. Say you took diamond as your reference structure and you define a distance metric from diamond. And you say, I'm going to look at structures that are very similar to diamond, say between 0.05 distance metric around diamond in similarity. So yes, you will have diamond and you'll have some diamond with some small distortions, but they will all more or less look like a diamond structure. So if you train and test on a data set that is sampled from there, you will have very low RMSEs, you will feel good, you have a really nice network, but it is really not generalizable. Because if you can follow this red line now with me, if you train in such a network, but then test on structures that are 0.1 distance away from diamond, you quickly see your RMSEs would explode. And if you go to even further and further structures where they are now starting to look much less like diamond, you will see that the error bars are very high. I don't think we talk enough about the structures that we train, the structures that we test, and how similar they are. So that's why we wanted to give some quantitative measure to that here. Every line that you see is a network that is trained on its distance data set. So the black line that you see is the neural network that was trained on the full data set, where it has all the crazy structures included, and tested on the full data set. And that, I think, gives a really more true measure of predictability. Because if you expect to make some predictive neural networks, you don't want them just to work in those few configurations that you trained on. Because you already know that configurations, you already did DFT on them. Like, what is the point? We want to have some generalizable potentials. We want to be able to predict things that happen at high temperature in maybe really big systems where different configurations can take place. So if you want to do something predictive, I think you should have a really rich structure to start with. Of course, not every application needs that. Sometimes you just want to do the same thing in bigger or same thing in longer time scales. Then maybe you're fine with having a limited data set. But if you want to really go for high accuracy, I think the richness of the data set really matters. And I would like to push for more people to use some distance metric to quantify how similar their test, train, validation sets are. Another thing I think that we always do, but we don't talk about enough, is RMSE. Our error distributions are almost never Gaussian. This is my experience with the networks that we have. Those distributions are almost never normal. So what is the point of looking at RMSE? Right, RMSE is meaningful for Gaussian distributions, but it could be very misleading for distributions with really heavy tails. And this is what we see here. The distribution has really heavy tails. And if I looked at the RMSE only, I would imagine the error distribution would be this green dashed line, while if I did a best Gaussian fit to my error, it would look like this black one. So these are very different error distributions, and just looking at one number RMSE is good for quick analysis, I think, but it doesn't really tell us the whole picture. So I would really always look at some more numbers or some distributions if I were you. Okay, Of course, the better thing to look at is always what is interesting to you in that physical system. Right here, we were looking at the energy ranking of hypothetical structures because we were interested in crystal structure prediction for this potential. And here, like the closer you are to the black line, that's DFT, the better it is. And the potential that we built seems to be the best among the ones that we have tested. Here is another example where we looked at the phonons. So phonons of graphite especially are very sensitive to forces to be calculated well. And we get a pretty decent one, I would say, even on the out of plane modes. Here is an even more sensitive system, but here there is a debate about DFT calculations being reliable or not. And this is a twisted bilayer graphene. It's twisted with a very tiny angle. So every atomic environment changes very little. So it's about like one degree difference. And we have results that agree with the DFT and the some other like very specific models that were built for this system with a neural network that was built with all those crazy structures that you have seen, but that has never seen a twisted bilayer system. So I would say we have a good level of generalizability out of this strategy. Another quick thing I'm going to show quickly, I don't want to take too much time from the tutorial, is molten salt. So sodium chloride molten salt is another thing that we worked on. We were interested in this for nuclear applications where you can have a very hot ion coming to this molten salt so that it cools down. That means you expect to have some local pockets with really high temperatures. This thing already melts around 1200 Kelvin, but you could imagine locally you will have temperature around 5000 Kelvin. So doing a potential for this is quite challenging because you want the potentials to be very smooth so that if you are going to do an MD run, you don't have to keep your time steps very, very small. You don't want to see the noises that come from the unsmoothness from a potential. So we had to work on this one with Gaussian activation functions in the network, which secure a potential that is very smooth. We built the data set ourselves just as physicists sitting down, like what kind of structures we should put in there. Again, not with any active learning or with some evolutionary algorithm, because we knew what would be the very challenging parts. So we knew that there will be a very high temperature liquid that network should be introduced to. So we put that in our data. We put some dimers in our data, really just two ions coming together in vacuum, because we know that there might be some interesting pockets happening inside the molten salt when the hot ion enters in the medium. But we could see as a result here, I will just show a few. Here is the experimental curve in blue that you see, and here is what we get with the neural network potential. And this is what people have been using, the classical force field, the Fumitoshi force field. So we have about 2 degrees off in the heat capacity, but we have the trend very right. That was a big success for this community. It's not so much my community, so I can't really comment, but they were very happy to have these trends, like heat capacity trends per temperature right. And another thing here to show, of course, when we look at the diffusion coefficients, we see that this blue one that you see is experimental prediction for this quantity, and the dashed green is DFT. So our results agree very well with DFT, but it is only as good as the DFT. So in, for example, the chlorine diffusion coefficient, DFT really is off from the experiment, so is the neural network. So we won't get any better than the underlying DFT, obviously. And if you have a potential that is specifically fit for something, some experimental quantity, it's always going to do better. And this was the case of this potential. And finally here, when you are doing a liquid calculation, you might never think that it makes sense to add there some dimer data. But we found it indeed to be very important to get this very short ranges where the atoms are really close to one another. You know, these are also charged ions actually. So there's a huge repulsion between them. We realized that putting this data, even a few data points, was very informative for the network to know what to do in this very high temperatures when ions get close to one another. Without this, we were seeing a lot of jumps or our MD calculations just losing total energy conservation because of the wrong integration. Okay, so this is all I wanted to tell. I hope this was enough motivation for you to learn a bit about PANNA. And now we can go to the deep note tutorial. I hope I didn't exceed too much my time, but so let's see if you can all see this with me.
Yeah, it was exactly 20 minutes. So
Yes, it's perfect.
yeah,
And,
I tried.
and we can see your deep note notebook.
You can also, I think, view this page, duplicate it on your space. Where we're going to start from is this tutorial 1 data prep notebook. You can go to the very top. The very first block you're going to see, you can skip it. This is, I just left it there. So if in the future you want to recreate this environment, the deep note environment that I recreated, these are the steps that you have to do. Some initialization, where to install, like the PANNA installation, which is a pip install. And I left a pre-release version of the code for you. We haven't done a release for a really long time, a public release. We've been working on our private repo, but this month is the month that we're making a new public release with a lot of the new features of PANNA and some optimization. So I put a version of this here for you. It's not the cleanest version. You know, if you're a developer, you know what I mean. There are some notes, some out there, some to do, some cleanups to do. But the code is the one that works. And okay, so let me see if we have other people joining on this document. Right, you can see the links to the document on chat. Thank you, Elena. Thank you, Venkat. We're going to start from this installation one, this block, where it says just after PANNA tutorial. You can either watch me or you can follow along. So I will just execute this. It's a standard pip install. The reason why I'm doing it here on the notebook and not in a terminal is because deep note puts them in 2 different places based on where you executed apparently. So I start from the notebook version. This should take just a few seconds. By the way, I have, if I am lucky, I have called one of my co-developers, Franco Pellegrini. Franco, are you here?
Yes, I am.
Yes. Okay. So if anyone that's following through has any issues, you can write Franco on chat and he could try to answer you about anything technical, you know, by the side. So don't hesitate, ask, he will answer you so that I continue with the standard tutorial. Okay, so we start with the idea that you have some data. It could be DFT data, it could be some other potentials data, you know, some force field data that's coming from lumps output. What we expect to see in your data is at least the atomic positions, total energies, and if you're going to use forces in your training, also the forces. PANNA does not have in this public version that you're going to see anything about stress. So you will only need atomic positions. That is coordinates, of course, so something that can set the potential and the energies and forces if you want. The general working style of PANNA is that we're going to write Python, some PANNA script, .py, and some input and output structure. This is how we are going to work with. This is a production run, I would say, rather than importing routines within PANNA and working in a notebook. Okay, so we will use some scripts which have their own configuration files, and we're going to just run one Python script at a time, just like that. Okay, so how do we start? I just placed some Quantum Espresso XML files here under PANNA data tutorial. You can see it here, PANNA data. You can see it when Deep Note is ready to open it for us. There's a directory called tutorial, and under here, there are a few I created just for this tutorial. You're going to create it as if you follow. There is one that says QE XMLs. Here, I just put some XML files. So these are Quantum Espresso suite of codes. If you use them, it's a DFT code. It writes out its high precision results, like at energy at every SCF step and such in these files. Of course, we don't need all this information from the Quantum Espresso. We need, the first thing that we do indeed is to extract this by a parser that is inside PANNA. we tell the parser where to find these XML files and where to write the example files. So example files are what we use in PANNA as really the necessary part from a configuration, a calculation. You run a simulation, what are the necessary things? So this parser is going to parse that. There is a lot of overhead. It doesn't scale with these few calculations, so don't worry. And where did it put it? Inside where we specified, which was my examples. So now if I run this, you're going to see we have an example. For each simulation we run, we have one example file. And if you want to see what the example files are like, you can just open them to read them. But because they are written in JSON format, you might want to see them in a JSON compatible reader. Sorry, like the JSON dump, just to show you what it looks like. It's a dictionary, so it says I have atoms. The first atom is an oxygen with this O. String defines it. This is atomic positions. This is an origin, looks like, and these are the forces. Second one is in hydrogen. These are its atomic positions, and these are forces. So you understand that this is an H2O, just a simple water molecule. We have a few other things, like what was the source file for that? What is the unit of length in this calculation? Are atomic positions in Cartesian coordinates or relative coordinates or such? We also mentioned that, and some lattice vectors. Finally, the total energy. So this is all we need from a DFT calculation, and it is parsed by PANNA. We also have a parser for VASP. We have parser for LAMPS. We don't have a parser for CASTEP because none of our collaborators use CASTEP. But if you're using CASTEP and you're into doing this, we can also prepare a parser for you. Okay, then next thing we're going to do is to convert these positions into a format that the neural network understands. We're going to use in this tutorial the Bellard-Parnello symmetry functions. Internally, we always call them G vectors. You might have heard them like symmetry functions. We will be using them in, I'm just going to show some pictures of it, but probably everyone knows about it already. In short, what they try to do is to sample the atomic environment of every atom with a Gaussian sampling function, Gaussian or something that looks like a Gaussian, that is most sensitive to atomic distances at a certain range. And you can have many of these sampling functions. Most of the time, to keep things local, you will have a cutoff so that it smoothly goes to zero. After a certain range, your atoms, the atomic environment information of the atom won't be provided to the network. Okay, so these are just local descriptors that are built by Gaussian sampling functions. This is the radial version, radial part, and this is actually how the equation really looks like. And just for two simple systems, I wanted to show you what the G vectors themselves look like. Here we have 32 sampling functions. You can think of like 32 bins of a histogrammed partial radial distribution function. This is what the diamond's radial distribution function histogram would look like, more or less, right? If you have a normalization, and this is more or less what the G vectors look like also. Instead, for a liquid, things are much less structured, right? You still have the first peak, but then you have atoms all around in many other distances. So it is not a crystalline. So we see that the sampling function picks that up too. These are like two different G vectors for two different structures. We have a similar thing for the angular part as well. For the angular part, we don't use Gaussians, but this cosine function, which is a similar structure, like a peak at a certain angle and then decays. What we introduce additionally to the angular part is actually a radial part as well. So our sampling functions are not only sensitive to a certain angle that this central atom is making with its neighbors, but also a certain average bond length in this angle. So it picks up different signals if you have a 60-degree angle, let's say, between your three atoms, and they are very close, so with its first neighbors maybe, versus some other configuration, a three-body term, where you have the central atom, and it is still 60 degrees, but your atoms are now, neighbors are farther away. So we just try to be sensitive of both angular and radial part at the same time in this part of the symmetry functions. This is, again, the more structured one is diamond, you see, and the less structured is the liquid. Every block here where you see R is the bins for average bond length, while within them we have the angular distribution. Okay, so this makes up a big vector that describes the atomic environment of each atom in the system. And there are quite a few parameters to fit. Maybe the most important ones are like how local do you want G vectors to be? So how much you want to have, how short-sighted or not your neural network to be. And the other ones is like how fine you want to put these sampling functions together, how fine you want these bins to be. And I put here some standard values that we have seen to work for many systems. I would say it is important, this part is important, but it has not been the bottleneck in our calculations. So unless you're choosing like very small parameters, like that make very, very small networks, you're most of the time safe. Trying it 2-3 values on the most important parameters seems to be working. Okay, so I will pass this part and just come to this section here, like how we are going to generate these G vectors from the example files that we have, these JSONs where the atomic positions were. It's again with a Python script. So we're going to use this time the gvect calculator.py script. And we're going to send it a configuration file that I put also configuration files all under the input files. You can see when you're checking this out in your own time. Let me show you here what the configuration files look like. So these are all the parameters that we want to use for this. These are eta, cutoff radius, etc. are exactly defined like in the equations. But we can also do some other things, like there are other symmetry function types that we implemented in PANNA, so you can define those. What are the species? Do you want to have the forces included? Then there are other keys here that I didn't add in this story because to keep this document very lean, and so you're relying on the defaults of a lot of things, but I think we set really good defaults. You can parallelize this process, and you can of course tell the code where to find the JSON files, the example files, and where to write the resulting G vectors. So let me just run this. I think I ran before this tutorial once, but. All right, so it tells me for the parameters that I have chosen, the vector size is 384. So for every atom in my unit cell, I expect to find a 384 size vector for this 4-species system. And it tells me that the type of the G vector is modified Beta Pernillo. And you can find the reference for the descriptor, then the paper that was explaining the descriptor. Okay, and if I do that, I'm going to find for every example file a binary file where the descriptor is held. So these are all, like each of them is for simulation 0, the binary file that holds the G vectors for that. And these are some other small molecules I put there from the ANI small molecule data set. And then we do one extra step, and this is we do that because PANNA is based on TensorFlow, and TensorFlow has a very efficient I/O. If you can pack your example files, all these things that you're going to use as input to the network in a format called TensorFlow record format, TFR, I'm going to call in short. So TFR allows us to put all these binary files very compact, very efficiently together, so the I/O stops being an issue for the training. And this is very simple script. You just need to tell where to find the files, where to write the TFR files once they are packaged, how many you want to put in one package. I just write here 10 because we have very few data. Normally what you want to do is around 100 megabytes, depending on your machine, but you can pack things like 100, 200 megabytes groups. And the script for this is the TFR packer. And I'm now showing you all the scripts one by one, but in a production run, you're going to have your own bash script that just runs these little Python scripts one at a time, one after another. Build parse my data, build my G vectors, pack them in the TFR files, and that will be all the data prep for you. So I run this too, and to show you, we have packed. Now we have these two TFR record files. One is like 1.2 megabytes, the other one is 181K. So in summary, your data prep is these three processes: parsing, G-vector calculation, and TFR packing. Do we have any questions about this? Okay. It's a little mechanical, maybe there is not much to think of, other than maybe choosing good parameters for your G-vectors. Now, the second part, come with me to tutorial 2 notebook, where we're going to do the training and validation.
Actually, sorry, I have a question. I
Go ahead.
probably just missed it. What kind of structures are we training on?
Oh, these are just some small molecules. I think I put there some water, some CH4. Yeah.
Okay, thank you.
No problem. Yeah, I just randomly put them there. Really, honestly, didn't check too much, but yes. In this step, what we're going to do is really defining a network, then training a network and validating. And these three things, we generally do them concurrently. We start with a network, we define something, we train, and in training, if we see that it is just too slow, it's not training well, maybe it's just too big, too expensive, we might just cut the training there and start with a new network. And or we might be validating, and you might see that in validation, we have some really bad results. Maybe we start with a too stringent data constraint, so we might add more data in between. So this is a more, I would say, less automated part of this from a human perspective. The setting of a network architecture is, again, we take configuration file in PANNA. So here is what configuration file of PANNA looks like. We're going to tell for training where to find the data, where the TFR files are. This is where we want to put all the training related information that TensorFlow is going to produce for us. For example, the resulting network, some checkpoints that it saves throughout, and we can define how many of them. Here is what kind of data we will be presenting to the network. So we say there are going to be 4 species, and we pack the data in this particular order, like HCON. We can give an output offset for every atom, because networks fit much better if we, I would say, when you start initializing your weights in a network, if you initialize them around 0 to small numbers, it will learn very quickly small numbers. So because these atoms, like if hydrogen total energy is about 13 eV, but oxygen is about 2000, there is really not much point in trying to learn these big numbers if the energy is only relative to some constant. So what we do the network, what we tell the network, like for every hydrogen that you see, take out this fixed reference energy from it, so that the total energies are never very big numbers, never very big ranges, but they all are around 0, like small numbers. Learning small numbers starting from small weights is just easier, just speeds up. It's not that network cannot learn if you didn't do that, but it's just quicker. Another thing, because we're built on TensorFlow, any kind of training algorithm that you can use in TensorFlow, we can use here. So we use, in this example, the default, which is an Atom algorithm. Is a stochastic. We're going to do also this stochastically, so mini batch learning. We are taking here 20 configurations at a time to update the weights with a starting learning rate of 0.01. And we're just going to stop this training once it makes this optimization steps at 1000 times. So this is a very short training. It's not realistic. If you want to do some production run, this is probably going to go to some, depending on your system, but something like 50,000, 100,000, those are more realistic training steps. Okay, and finally, we want to define the network. Here we say, okay, this network has an input 384. So that was the G-vector size. That is the input layer size. And then we have 2 hidden layers, 128 and 32, and 1 output layer for every species. And if we wanted to freeze a part of the network, we could just turn them off in this trainable key. We don't want to freeze anything. We are just starting from scratch. So all layers of this network are going to be trainable. And this is a simple way of setting neural network architecture to be trained. If we wanted to have different architectures for different species, we could also define it here. Like we want maybe carbon to have a more complex network, hydrogen network to be a smaller network and such. Okay, so if I just put these like the highlighted parts, we are defining here a simple fully connected network. This is not the only network type available in PANNA, but the one that is the most used, the one I showed examples on. We set the parameters for the training. Sorry. Okay, I lost my cursor. Okay, so we also set some parameters of training like learning rate, which learning algorithm we want to use, etc. Then we can set many other things about parallelization. I didn't put there. Different kinds of loss functions I didn't put there. So many things that you can think of doing with TensorFlow, you can do with PANNA. So that allows you to have access to really, I think, state-of-the-art algorithms, which is good. And finally, if I run this training, this is what the results look like. So let me run. Okay. You see, now this is going to be empty. Okay, so it was here. So I have to enter in the tutorial.
I believe you have it in a cell below.
Do I have it below?
Yeah.
I can just copy the, okay. Yes, thank you. I can do it from here then. I'll just run it from here. So because TensorFlow produces some output files exactly at the running location, I just made myself a new folder called my train logs, and I'm just running the script from there. And the script that I'm running is train.py. So if you remember in the earlier step, we have G-vector calculator, so parser, G-vector calculator, TFR packer, and here we have train.py. And the input to this is the configuration file that I just showed you about. And if I run this, you're going to see how the training goes. This is just TensorFlow understood what it needs to do. Here is some messages, some info messages that it gives us, because it could be just way more optimized compared to what this deep node machine we have access to. And here the training has ended, just made 1,000 steps. So 1,000 steps, 20 configurations each. They were quantum espresso small molecule results. And it's just very fast. Actually, all the time that you have seen is mostly the overhead. It can work with much larger data set and much larger networks. And yes, here is the production, like what is the output of this training. You see a lot of checkpoints. These are the checkpoints that TensorFlow gives us. So it is at that point, let's say step 1,000, what was the network like, what are the weights and biases of the network, and some other information that allows you to restart from this checkpoint if you want it. We don't look at the data that comes out of this by eye. Most of the time, what we do is to look at the tensor board. So tensor board, I don't know how many of you are familiar, but if you want to use tensor board, you need to do something on deep node. You need to come to the environment tab and allow the incoming connections, because tensor board is going to visualize these tensors that were built, the networks that were built in a browser. So we need to allow the connection, which will show you an address here. So just copy this address and paste it somewhere. And if you click it, sorry, my address, I think it's the same address. Let's see if my files are there. Let me see if it's the same address here.
You have not started TensorBoard.
Ah, my bad, my bad. There's my TensorBoard run, exactly. So the way of running the TensorBoard is this TensorBoard command. When we have installed TensorFlow, we also installed TensorBoard there. We need to tell where to find the training information. That is the my train that we have defined. You need to give a host and port. In this environment, normally it will find from default 3 diva. So let me start. this visualizer, it started, and that means it started writing in this address what it found from the training. Can you see my screen? Okay, so what is this? This is all the tensors that we have saved during training visualized for us. There are a few ways of visualizing. So we're going to start from the scalars. Scalars are the things that we told TensorFlow to keep track of throughout the training. For example, the loss. This is the energy loss. TensorFlow tries to smooth these things for us. So let's reduce the smoothing a bit. This is how the energy loss on energy changed during training. We didn't use regularization like L1, L2 regularization. So there is nothing to see regularization loss. So total loss is equal to the energy loss. The lower this number goes, the better your training is going. So your network is learning something, your loss is reducing. I generally go to the logarithmic scale here to see how it was going. So you're looking at the first 1,000 steps, right? It was going down and maybe with some noise in between. It's a very limited training. Other things that we look at more carefully is that this loss just the default loss. Just the default loss, meaning it was a delta E square calculation. So for every ground truth example, every DFT simulation we have, we take the difference between what the ground truth is, what the network's prediction is, take the difference and just square it. But you might want to see other things. For example, the standard deviation on the error of the energy or per atom, right? Because you are sometimes interested in per atom energy. You might have in your data some molecules that are very big, some molecules that are very small. You don't want to see just the errors, standard deviation error on all structures. You're interested in the per atom energy, and this is where you would look at. What else we could see here? Sorry, let me move this Zoom interface up. You might want to see what is the mean energy that the network finds for each species. So carbons that you see in all these 10 structures we have, on average, seem to be energies around like 9. And this is more like a sanity check kind of panel. You don't want that the energy of a certain species stays the same throughout the training. That would mean, like, independent of which batch of structures I'm looking at, network is really not learning anything about that atom. It's always just giving me a constant number, because a carbon that is in one molecule is going to have a different contribution to the total energy in another compared to another molecule that has a different environment, right? If you're looking at a CH4 versus a carbonic acid, you're going to see very different contributions that are coming from carbon. So you want to see some variation here. This is more or less sanity check. And there are other things that you can look at, like how the number of atoms changed throughout your training in different batches, because we're randomly picking these batches. So there's going to be some variation. If you are into graph computation, you might want to look at what the graphs look like. These are the 3 layers. I think this is way too tiny, maybe not so much of an interest for this audience. The 3 layers for hydrogen network, 3 layers for carbon network and such. I will pass to this histograms. So now you can see how the weights changed, how the weights of each layer changed throughout training. So this is carbon network's first layer, like the 0th layer, the one that is closest to our input. What I can tell you by looking at this is that it actually didn't really learn anything. It's more or less where we have initialized. This is going to probably take more training for the update on the weights to change, to make a change on this first closest layer to the input. But if you look at the other layers, for example, first layer, here already we are now in this layer that was like 128 nodes. Here we already see that we initialized the weight somewhere, but it changed during training. And it will show some small modifications here on as well. And this is the one that's now closest to the output. This also quickly, the back propagation updated these weights. So we have, so this network needs to really run more so that we have some more information learned by these early layers too. And this is the same thing for hydrogen. You can see that the bias of the hydrogen network is still changing. So this network will still learn some more. You can look at the same thing for nitrogen, for oxygen. And if you want to do some kind of analysis, like people do weight analysis, you can see these are the weights on a PCA. I don't know if they're too tiny or if you can actually see. So this is a PCA that's made on automatically on the 0th layer of the carbon. Some weights are distinguishing themselves. So those are the ones that are spherically distributed. But a lot of the weights are just accumulated in this point because they most likely are the ones that are very similar to their initial values that really did not change. When more training steps happen, backpropagation is going to also move these weights from outside this spot, but it is not there yet. Indeed, if I compare it to, let's say first layer. In first layer, we already see that the weights are not that much, or maybe I go to a 2D, might be better. The weights are not all accumulated in one spot and they're not all the same. You know, they are in this 32-dimensional space, but they have a distribution. So some learning has happened in this layer. Okay, there's a lot of analysis that you can do by looking at TensorBoard. You can do TSNE and such, but I'm going to come back to our tutorial. And because TensorBoard does not stop by itself on deep node, we have to stop the execution ourselves. Okay, so you can stop the execution of this block and do some more standard validation. For validation, what I do is that I put some of my TF records to another folder called, these are my validation files. The validation configuration input is also similar. It's simple. It says, where is my data? Where is my network that I'm going to validate? And you can tell, like, okay, validate every checkpoint that you have saved throughout the training, or you can say validate only the very last network that you have reached. You can give this information as you like, but depending on whatever you want to check. And if I run this again with the evaluate.py, this is our validation script. See? Okay, it says it might take a while, but actually it's just like a blink of an eye. So this is already finished. We validated our network, meaning we evaluated this network on some new data that we have not seen before during training. And we have just done it for the very last step of the training. So step 10,000, step 1,000, sorry. And information is written to this dot file. What is written there? I just kept it lean by not writing the file names here, but you can see it writes how many atoms are there in this configuration, what is the DFT energy, so the reference energy, the ground truth, and what is the energy that the network estimated for that. So we did not use forces for this. If we had forces, then there will be here 3 columns, 3 columns in this document for average, but in other files, there will be a list of forces too. So you could have access to all the forces that the reference has and all the forces that the neural network predicts. We generally don't look at these things by eye, but we just plot them to see. So this is a simple plot of the difference between the DFT and the neural network and the configuration index, meaning the structures that we have done this validation on. This is all a very mock size example. Of course, I have just 180 configurations of small molecules here that has CHON. I trained a very mock network here, so nothing is really expected to work. And despite that, it looks like because my train and validation sets are rather similar, they're coming from a similar kind of source, the error is not too crazy. I would have expected worse from such a thing, but still we are staying within like 20 MeV per atom. It's a ridiculously small amount of data for such a network. Okay, any questions about this? If not, I'm going to the last part.
I think that we are more or less out with time.
Okay, so the last part is the simplest part. Is if you come to the last tutorial notebook there, it looks long, but it's actually very simple. It is basically saying, okay, so you trained, you like what you have seen, you like your validation. How are you going to take this potential, take this network outside the TensorFlow and use it elsewhere? And this elsewhere can be lumps, this elsewhere can be GROMACS, whatever you like. For that, we have a script called extract weights. And this is what its configuration file looks like. We are telling where to find the network, which checkpoint, which network among all the ones that might have been saved is the one that you want to convert, and what format do you want to convert. So if you convert to PANNA format, that is compatible with OpenKim. And OpenKim, I don't know if you're familiar, makes an interface for potentials with multiple MD codes. But you could also use something, if you're only using lumps, you could also just say, I want it to be extracted in lumps format. That extracts the network for you, writes it in a binary file. And if I run it here quickly, you can say like the weights, the network saved in lumps weights. And now I can see what is inside lumps weights. You can see for carbon, hydrogen, nitrogen, oxygen, the data in binary, so the network structure, the weights, etc. And it also comes with this in file that basically a file that you can rename differently if you like, but it is going to tell lumps where to find this information, like where to look for carbon potential, where to look for oxygen potential. And I will pass this and just show you how to use this information in lumps. Here in a lump sample lumps input, there it is. So you have to say pair style PANNA, pair coefficients is in the directory that you defined. I just called mine parameters, and this is the weights.out or panna.in, depending on how you name this file that I have just shown you before. This file that the extractor provides you. So that is a way of using everything within lumps. And you can also run this small lump script that I provided. I have run it quickly. Maybe I can show you. It was just an MD run, but okay, so everyone knows how to run, I think, their own MD. And now you can go and use your potential to do any MD that you want to do. Okay, I'll cut here for time. Any questions I would be happy to answer here or on Slack later on.
I think that we can have some time for questions if someone wants. Yes, you see Nong.
Hi, Nong.
Hey, Emine, good to see you. Thank you very much. Very nice talk. I have questions on the molten salt. If you could share the slides again, because I forgot you show so many things. I'm curious about like how long that you run MD simulation until you get really, this is like a melting. Maybe I missed this part. So this is very, wow, it's very nice work. So you are saying that the data set that you have, and then you use it in many different temperature, high temperature, and zero everything.
This is where our data comes from. So we have in this data set 100,000, 112,000 DFT calculations. It's a giant data set. So 60% of them comes from liquid snapshots, some MD liquid snapshots in various temperatures, but like more normal temperatures, say. When we say high T liquid or high T crystal, we are going to, for high T crystal, we are still not melting, but we are close to melting. But for high T liquid, we went even up to 20K. So some configurations that come from 20K, 20,000 Kelvin. So at 20,000 Kelvin, you have these very strange configurations. And those are sampled from partly DFT calculations, partly the lumps calculations for other force field, because we need a huge range of environments. And we use them. We didn't use too much of them, but even using a few really enriched the network's results. It really made the network's result better, enriched the data set.
I see, I see. So in total, like how long did you run MD simulation until you really see the sodium chloride really melt and break here? I'm just curious about the time scale.
Well, good question. So I actually don't remember how long we ran these.
It's very long, right? Until it's melting from crystals and then it's melting. Yeah,
definitely. If you just try to get the, if you're not using any acceleration process, it takes a long time to see the melting. And we didn't see the full cell melting. We have seen enough that we could extrapolate. So how you do these calculations generally, you know better than me probably, but you have the crystal side, you have the liquid side, and you see the interface moving. So we could see the interface moving for long enough. Now I can't really remember.
That's fine. I can check your paper.
Hundreds picoseconds or so.
I can see more hands writing. Thank you very much.
Thank you. Yeah, so we could see half of the cell melting, but we didn't go all the way melting and back. Yeah, thank you. I should know these numbers. It has been a while. Yes.
We have another question by Sander.
Hi, yeah, thank you for the demonstration. So I was wondering what your thoughts are on how PANNA compares to like message passing architectures like SNET or like FISNet or, you know, DimeNet, all these, you know, variety of models that have emerged in more recent years. Like, how would you say in terms of like the training time that's necessary and the amount of data that you need to reach a given accuracy, how does this model compare to those?
Honestly, I never used SNET, but we have another version of PANNA that we do message passing. By message passing, basically what we do is that you look at some layers, and instead of trying to just connect networks with just layer information weights, we connect them through other channels too, so that you can transfer some information that would not be transferred otherwise, right? So we have had networks like that. One worked really well on small molecules. And I think this is also where you see the strength of SNET, organic structures, where you can really locally understand something and then carry that information to the next layer. This is also why chemists are so good in, you know, coarse graining, you know, because you can look at that structure that maybe a few layers, few information, and there is something there. When I try to do this, again, inside PANNA, so not in SNET, maybe SNET does it better, I don't know. When I try to do this in crystals, my experience was that there is really not much message passing because the information is everywhere in the crystal. Like if you're really trying to, let's say the accuracy and the efficiency are like more or less like a fully connected network. Because the information requires many enlarged field of view if you want. Because you need so many atoms to make a flake that describes the graphene if you want. You see what I mean? Like you need those local message passing does not really help. You need to go to deeper layers. So in one case, I had to go to like 50 layers of processing so that my field of view was large enough so that the message I was passing was meaningful and helped with the accuracy. At that point, a simple fully connected network was just much simpler. But if you're doing molecules, I think it's a good idea.
Okay. Thank you.
Thank you. I don't see any other hands, and I'm sorry I took like extra time, but
no problem. So if there are no more questions, I think that I can stop the recording now.
Now maybe you can